So what we're going to set up today is the idea of conservation of energy. So fundamentally, one way that you can explain conservation of energy is simply the statement that energy is never created or destroyed. So what we can do is we can change the form it's in, we can change where it's located within a system, we can add some to a system, we can take it away from a system, but we can't just sort of create it out of nothing and we can't make it disappear. So what we're going to do then is we're going to keep track of the energy within a problem by thinking about sort of three different terms here. One is the initial energy of your system. The second one's the energy that you either add or subtract from your system. And then the final energy of your system. And so you notice that what this equation is basically telling us is we're going to start with some amount of energy. We're going to add or subtract from that, and that's going to leave us with what we've got at the end. So this basically is giving us a schema for keeping track of the energy. So it tells us that energy is transferred, so we can transfer energy from one form to another within our system. That's literally just sort of reshuffling how it's stored within our E's here. Or we can transfer it into or out of the system, and all that happens through work. So we'll see that there are forces that can do work that will change the way the energy is stored within our system, or forces that can do work to either add energy or take energy away from our system. So building off of this equation, one of the things we notice is if the work done by non-conservative forces, if that term is zero, then what that means is the initial energy and the final energy of our system are the same. So saying that the energy of the system is the same is another way of saying it's constant. And the fancier way we have to say this is this means that the energy of our system is conserved. So what we're going to keep track of at this point in the course, right? So we'll add on different types of energy as we go further into the class. But right now, where we're dealing really with mechanics, right? We're in the region of physics dealing with mechanics, so we're interested in total mechanical energy, and this is defined to be just the kinetic energy plus the potential. So what this means is my energy equation here, the way that I'm keeping track of what's going on with the energy, we'll label our energy balance equation, and basically it says that we're going to have some initial energy that can be located in either kinetic or potential energy. We'll have the ability to add or subtract energy from our system, and then that'll let us keep track of the final energy as it's stored in either kinetic or potential. So this is going to be our energy balance equation that we'll use, and we know that when our work by non-conservative forces term is zero, and that tells us that energy is conserved for that particular system. So what types of energy are we going to need to keep track of? Well, there's a couple different types of kinetic energy. The first one, of course, is going to be translational kinetic energy. This is the energy due to the motion of the center of mass of an object. There's a second type of kinetic energy that we'll see when we start dealing with how things rotate, and that's the rotational kinetic energy. So that's energy due to rotation of an object about its center of mass. So again, our kinetic energies are largely keeping track of the energy due to motion. We just have different ways in which our object can move. Its center of mass can move, it can rotate about its center of mass. So how do we keep track of the work done by all the forces? Well, we're going to do that by thinking about the work done. And so a couple of ways that we can think about the work done, or we can think about the work done by a couple of special forces by thinking about our potential energy terms. So the potential energy terms are gravitational potential energy. That helps us keep track of the work done by the gravitational force. Elastic potential energy will help us keep track of work done by the spring force. And then our work done by non-conservative forces term is going to let us keep track of the work done by everything else. So again, in our in where we're at right now, we simply have two conservative forces that we can keep track of the work done by those conservative forces as potential energies. Everything else is non-conservative, And it's either, and all the rest of those, so all the rest of those forces will either add or subtract energy from the system. All right, so the strategy that we're going to use in terms of solving problems with our energy balance equation. So this is typically what we're going to think of as solving our conservation of energy problems. Well, we're going to start by drawing two sketches. So we're going to draw the initial configuration, we're going to draw the final configuration. We're going to identify which forms of energy we need to keep track of. So is the center of mass moving? If the answer to that is yes, then we'll keep track of translational kinetic energy. That's the kinetic energy that we know at this point. Is the object rotating? Well, if the answer is yes, then we'll keep track of rotational kinetic energy. So when we start to add rotational motion, this will add this new question. Does the object move up or down? Really what we mean is, does the center of mass of the object move up or down? Does it change heights? If the answer is yes, then we'll keep track of gravitational potential energy. Does our object compress or stretch a spring? If the answer is yes, then we'll keep track of an elastic potential energy. So these are the questions that we'll use to help us figure out which forms of energy we need to keep track of. Is there more than one object in the system? So again, it may be that, hey, I've got two objects that are moving, and they're both changing in height. Or two objects that are both moving, but only one of them is changing in height. So again, I'll have to ask my set of questions for each object within the system. Once I've figured out which potential energies I need to keep track of, then I need to identify where the potential energy equals zero. So again, we'll get used to sort of picking where the potential energy equals zero for gravitational potential energy. And then we'll always use equilibrium to be where the elastic potential energy equals zero. But we need to identify what those points are on top of our sketches. Then we'll set up our energy balance equation. We'll basically say, okay, how can I determine the initial and final kinetic energies? How can I determine the initial and final potential energies? So we'll get the initial and final energies for each possible type of energy in our problem. We'll calculate any work done by non-conservative forces. So again, if we have non-conservative forces in our problem, then we need to do that calculation. And then last but not least, we'll solve for what our unknown is in the problem. So we'll see this strategy, and again, when we come to class, this is basically what we're going to spend the next couple of class sessions on, working our conservation of energy problems using our energy balance equation.